Depth-first traversal, or depth-first search, is another way to traverse a graph. The difference between breadth-first traversal and DFT is the order in which the nodes are traversed. In BFT, we visit all the nodes in the same level before visiting nodes further from the root. In DFT, we first move as far away from the root as possible, backtrack until we see an unvisited neighbor, and repeat. Consider again the following graph. As before, we can represent the graph as a stack of edges. Let's again construct a spanning tree, but using DFT instead of BFT. We will use two stacks. The first stack will contain the spanning tree, and the other tree will store adjacent nodes or neighbors. Both stacks contain nodes. The node consists of the node value and its parent node value. Here's an outline of the DFT algorithm. Step 1. Push the root node to the neighbor stack. Step 2. Pop an element from the neighbor stack. Step 3. If the spanning tree already contains the popped node, then discard it and go back to step 2. Else, push the node to the spanning tree and go to step 4. Step 4. Find the neighbors of the top element in the spanning tree. Step 5. Push the neighbors that are not already in the spanning tree to the neighbor stack. Step 6. Repeat steps 2 to 5 until the neighbor stack is empty. Let's use this algorithm to build a spanning tree starting from Paris. The two stacks are initially empty. First, we push Paris to the neighbor stack. Then we pop Paris and push it to the spanning tree. Then we look for neighbors of the top element in the spanning tree, which is Paris. Paris's neighbors are London, Brussels, Barcelona, and Milan. None of them are in the spanning tree yet, so push all of them to the neighbor stack. Now we can start the next iteration. First, we move the top element in the neighbor stack, Milan, to the spanning tree. Then we find the neighbors of the top element in the spanning tree, which is Milan. Milan's neighbors are Paris, Munich, and Barcelona. Paris is already in the spanning tree, so we skip it. We push Munich and Barcelona into the stack. Next, let's visit Barcelona. First, we move Barcelona from the neighbor stack to the spanning tree. Then we find Barcelona's neighbors, which are Paris and Milan. Paris and Milan are already in the tree, so we skip them. No new nodes are added to the neighbor stack. We've hit a dead end, so we visit Milan's second neighbor, which is Munich. We pop Munich and push it to the spanning tree. Now we find Munich's neighbors, which are Brussels and Milan. We push Brussels into the neighbor stack. Milan is already in the tree, so we skip it. Next, we pop Brussels from the neighbor stack and push it to the spanning tree. Then we find Brussels' neighbors, which are Paris, Amsterdam, and Munich. Paris and Munich are already in the tree, so we skip them, and push Amsterdam to the neighbor stack. The top element from the neighbor stack is now Amsterdam. We move Amsterdam to the spanning tree, then look for Amsterdam's neighbors. Amsterdam's neighbors are London and Brussels. Brussels is already in this tree, so we skip it, but we push London to the neighbor stack. Then we start the next iteration. We pop London from the neighbor stack and push it to the spanning tree. First, we find the neighbors of London. London's neighbors are Paris and Amsterdam. Paris and Amsterdam are both already in the tree, so we skip them. No new nodes are added to the neighbor stack. We went as far as we can go, so we backtrack again. But notice that the remaining nodes in the neighbor stack, Barcelona, Brussels, and London, are all already in the tree. Thus we are finished. Here's a video demonstration of the algorithm.